What is the nth term in the Taylor expansion of the cosine function around b is equal to 0? I really like this problem. Just saying. Now, the cosine function is a very interesting one. I would like to start immediately by computing the value of the function at 0. Because this will be useful. This will give me e to the 0 plus e to the minus 0 divided by 2. This gives me 1. Okay, what about cosine prime of 0? What does it give me? Well, you can check. First off, the derivative is going to be a half, and then e to the x is e to the x, and e to the minus x, when you take the derivative, it becomes minus e to the minus x. When you plug in the 0 here and then plug in the 0 there, you get a 0, actually. So that is what we will get here. You see, it's because the derivative of e to the x is e to the x, and the derivative of e to the minus x is the same thing, but with the minus. So when I plug in 0, I get the 0. Okay, but what is the second derivative of cosine of x at 0? That's a good question, right? That is going to be just the derivative of this thing, which is, well, e to the x is e to the x. And now if you take the derivative of e to the minus x twice, you get e to the x. If you take the derivative of e to the minus x twice, you get e to the minus x again, which gives me cosine of 0. So this is equal to cosine of 0. And cosine of 0 is equal to 1. So in principle, all even powered derivatives are equal to 1, and all odd powered derivatives are equal to 0. So these are our findings. So all even, let's say k, derivatives at 0 of our function. So if I call this f, gives me 1, and all odd derivatives at 0 are 0. Now it is a good idea to start writing down the Taylor expansion, which is given by a sum from k is equal to 0 until n. It's a Taylor polynomial, x minus b, which is the point at which you expand your polynomial at, the power of k always. We're always dividing by k factorial, and on top we have the derivatives. So the derivatives determine the coefficients of this polynomial. But not just the derivatives, we need to evaluate them at our point b. So b is equal to 0. This is already something we know. I'll just write x. And we have this very interesting fact. So we could, in principle, write this as a sum. Well, two sums. First off, to be clear, we are writing the expansion of f of x, which is cosine of x. And this is not equal to n on the nose. This is an approximation. We know about this. I mean, there's a remainder term, but we don't write it. So I just suffice myself with this approximation symbol. So x to the k is here, fk of 0, and then k factorial. Maybe it's even better if I do it like this. I would like to write this sum as two sums. So from k is equal to 0 until, well, n over 2. If it's an even number, because it could be an odd number, right? And then this is just a technicality. You can ignore it. I mean, you can just ignore it, okay? You just say k even over k factorial plus k odd. I forgot to include the right. I mean, in principle, I should be able to write this because, I mean, if you have a bunch of numbers, you know, half of them are even and half of them are odd. We're talking about the numbers k, which vary from 0 to n. And the good news is that this, for odd k, it goes to 0. So this whole thing is 0. We don't need it. We just need the even terms. Isn't that just amazing? And if that is the case, then I can write this as a sum from k is equal to 0 to n over 2. Okay, this is a technicality again. I use the floor function, which gives me the integer. So if this is 5, it will give me until 2. And I write x to the 2k divided by k factorial times the value when fk of 0 is even, which is equal to 1. And the only case where this is even, again, is when this is multiplied by 2. So you get all the even numbers from there. And this is basically what's happening. And if you're wondering what happens, I mean, you could in principle take a limit to infinity, do whatever you want. But if you would like to describe the nth term, or let's now say the kth term, then the kth term is given by x to the 2k divided by 2k factorial, simply because all the odd terms cancel out and all the even terms, as you can see, they double in this very specific way. If you add the half and the half, you get the 1. This is all I have to say. The cosine function is very interesting. If you take the derivative of it itself twice, you get the same function again. So it's like sine and cosine, but without the minuses that appear. So very interesting functions, very cool functions. Maybe we'll talk about them in another discussion.